Welcome to EDU World Space.
Problem 7.65. We have a package handling system where we have a box that's being placed in front of a compressed spring, and the spring is then released, and it pushes the box on a surface that has a coefficient of friction of 0.3. We're told some information about all this. The initial compression of the spring is 0.28 meters. And what we'd like to know is what is the speed of the box as it leaves the spring, and what is the maximum speed that the box obtains. So we know that the box starts from rest, and so the initial energy must all be potential. Kx squared, and then work done on it by friction, mu, and then the normal force is just its weight, times say x naught, because this moves a distance of the 0.28 meters before it clears the spring, and that's the moment where we're wanting to find the speed for. And then this is equal to the kinetic energy at that moment. And so you solve this for v squared, put in the numbers, and you find that its speed is 0.747 meters per second. Now, let's have a variable x that's the distance when that's the distance along which the box has traveled, and we want to maximize the speed as a function of that. So, and then x naught will be the initial compressed length. So we have 1/2 k x naught squared minus mu mg. Now this time we have x naught minus x, and then we have 1/2 mv squared plus 1/2 kx squared. X decreases as the box moves because x is the amount of compression of the spring. So when it clears the spring, it will have done all of this work, and it linearly increases up to that point. And similarly, this goes down to 0 as the spring expands. So now we want to find a maximum of this for v squared. So we want to, and the reason we can take just v squared is that it's less work for us. So you don't have to take the square root, and that makes the derivatives a lot more complicated. And because the squaring something, if it's always positive to begin with, like speed is, then squaring it preserves the ordering of it, so it doesn't cause it. So the maxima of v are going to be the maxima of v squared, basically. Excuse me. So anyway, we want to maximize it, set that to 0. And evaluating the derivative, we get negative 2kx, kx, plus 2 mu mg. And then we solve this for x max, is what we'll call the position that maximizes the speed. And that will be mu mg over k. Substitute this back into this expression after you've solved it for v squared. And so then you'll find that Vmax is equal to 0.931 meters per second. And so it is the case that depending on what the coefficient of friction and the spring constant is, that it will reach its maximum speed sometime before it stops being forced by the spring, which makes sense because the force of friction is acting against the spring. The strength of the spring is decreasing as it expands. And so at some point it's going to reach a peak and then start coming down. And so you can see that unless the friction goes to 0 or the spring constant is infinite, that's going to be somewhere before it reaches the end. Because recall x max, or x is the amount the spring is compressed. So x max being 0 would mean that the speed is greatest right at the moment when the box is free of the spring.